So next, everyone, I'd like to introduce you to Dr. Mike McCullough, who just came in. He'll be discussing quantized inertia and the horizon drive. Mike has a bachelor's in physics from the University of York, a PhD in physical oceanography from the University of Liverpool, and currently lectures in geomatics at the University of Plymouth. He's a member of the British Interplanetary Society, the Lifeboat Foundation, and a fellow of the Higher Education Academy. And he's published dozens of papers on physics and geophysics in numerous journals. We've had a lot of requests to have Mike present at APEC on quantized inertia and the horizon drive. So I'm really pleased that he's able to join us and speak about it today.
Okay, so today I'm going to be talking about quantized inertia. So I'll first go into a bit of the background. What is inertia? What do we think it is? Then I'm going to propose a new theory for it called quantized inertia, discuss the astronomical evidence that I've managed to collect so far, talk about the DARPA funding I received to test it in the lab for thrust, talk about horizon drives and their applications at the end. Okay. So I guess I don't really need to go into this because Tim already went through this. So this is my background. You can say I was also a scientist at the Met Office and ocean forecasting. So I have a background in the ocean, and some of my thinking in physics comes from my previous experience studying ocean waves. Okay. So the basic problem I started off with was the well-known galaxy rotation problem. So as you know, this is a galaxy. This is the Andromeda galaxy, and it's spinning around, all the stars and it's spinning around. And they've managed to calculate the amount of mass in a galaxy by looking at the number of dots in it, and assuming each one has the mass of the sun, you can work out the mass. And then they can look at the velocity of the stars using Doppler shift and work out their speed and the centrifugal force that they are experiencing outwards. And it turns out that the gravitational attraction is far too small to hold the stars in. So all the galaxies we see should be flying apart, but they aren't, obviously. So this was first noticed by Fritz Zwicky, who's shown on the bottom left in 1933. And more recently, with galaxies themselves, Fritz Zwicky was looking at galaxy clusters by Vera Rubin in the 1980s. Okay, so what's normally done in astronomy is to add dark matter to the galaxies to increase the gravitational force inwards to hold the stars in. But dark matter has to be adjusted to fit every galaxy, so I don't regard this as being good science. Other reasons for doubting dark matter, there's a list here. So, for example, there's something called Renzo's rule, where speed follows the light. Every time there's a change in the speed of stars and galaxies, there's also a change in the light curve, or the amount of light in the area. So it seems that speed follows the light and there's nothing dark affecting it. I'll talk about Milgrom's break, what I call Milgrom's break, a bit later. But also other smaller systems like globular clusters and wide binaries within galaxies, they can't contain dark matter, which must remain smooth on those scales. But they show the same anomalies as well, which argues against dark matter. And also a philosophical point, dark matter is not falsifiable. You can look forever for more exotic dark matter particles and get funded to do so. And you can go on forever like that. Okay. So I started thinking about inertial mass. So inertia has never been understood. It's just assumed that things keep going in straight lines until you stop them with force. For example, this ladder keeps going in a straight line when the van stops. Inertial mass is not due to the Higgs field, which only explains the mass of the quarks, which is about 0.1% of the mass. So what I'm going to do is propose a new model for inertia, which combines some aspects of relativity and quantum mechanics. Okay, so first of all, quantum mechanics. So the Heisenberg uncertainty principle. So this is quite famous and is shown at the top here. It says that the uncertainty in momentum of a quantum particle times the uncertainty in its position has to be more than a very small number. So what this means effectively is that if you shrink the spatial scale that you're looking at, so you shrink the uncertainty in position, then you increase the uncertainty in momentum. So this means that on the smaller scale, space is teeming with virtual particles, which they can be thought of as particles appearing in pairs, as shown by these blue arrows here, or they can be thought of as waves, shown by the red wave here. So space on the smaller scales is a bit like an ocean. So is this true? Well, Hendrik Casimir proposed a test for this. He said that if this is true, and you put two plates very close side by side, then some of these quantum waves would fit well between the plates, for example, this one at the top, and some wouldn't. So you see the one in the center here, there's an antinode at the plate, so the electrons in the plate will move around to damp the wave, and so some of these waves will be cancelled between the plates. And this means that there'll be more quantum vacuum pushing the plates together than will be pushing them apart, so they will tend to move together. And this is called the Casimir effect, and it has been well observed now. It was observed first in 1996. Okay, so it seems that on the smaller scale, space is a bit like the ocean. So I'm going to try and present you a simple analogy now. This isn't meant to be exact, it's just an analogy. If you imagine a ship parked next to a dock, then out to sea there'll be lots of waves hitting the ship, giving it momentum and pushing it towards the dock. But the idea is that between the ship and the dock, there will be fewer waves because, first of all, there'll be sheltering, but I'm not so concerned about that. There will be a kind of resonance in that only certain waves can exist. For example, the one shown can exist because it's got a node, a place, part of the wave where the water doesn't move at the ship and the dock, so there's no friction, so this wave can continue to exist, but other ones are damped. So there'll be more waves out to sea, so the ship will tend to move towards the dock. And in fact, there's something called a maritime Casimir effect. In the ocean, two ships side by side will tend to move together because of this effect. So in this case, the ship will move towards the dock, and if the people aren't aware of the waves, then they will assume something mysterious. And I think this is how we regard inertia at the moment. Okay, so in order to go a bit further, I have to replace the dock damping waves with something a little bit more abstract, and that's a horizon. So imagine you have a rocket which is accelerating to the right here, shown by this black shape, and it's accelerating so fast that even if an explosion happens behind it, the sound from the explosion will never catch up to the rocket. Then from the point of view of the rocket, the explosion does not exist. So you could say that the explosion is behind an acoustic horizon for that object. So this is the idea of a horizon. It's sort of a boundary to the cosmos that we can know about, and it doesn't just work for the speed of sound. It also works for light. In that if the rocket accelerates fast enough, then even the light from the explosion will not catch up with it. So a horizon is not a physical thing, but in what follows, I'm going to treat it as if it was. Okay, so these horizons have been looked at before. So for example, Stephen Hawking wondered what would happen if one of these virtual particle pairs was emitted on a black hole event horizon. So if you have a lot of mass in a particular region of space, light cannot escape from this so-called black hole. And if you have a virtual particle pair emitted right on the boundary, the one that goes into the black hole will disappear, which will leave its twin free to be released as what's now called Hawking radiation. Just a couple of years after this, Bill Unruh from Canada, who's shown in the top right here, said that a similar thing happens to an accelerating spaceship or any accelerating object, in that a certain point behind it, in the area on the left, information will never be able to catch up to that spaceship traveling at the speed of light, limited to the speed of light as it is in special relativity. So again, if you have a particle pair emitted right on this horizon here, the one that goes behind the horizon will disappear, and the other one will then be free to be released as what's now called Unruh radiation. So this is a very interesting kind of radiation because it would be seen by the accelerating spaceship that somebody standing still or going at constant speed in the same space would not see the radiation at all. Okay, so has this been seen? Well, it may have been. The problem with seeing Unruh radiation is that the wavelength is very long for the accelerations we experience. So for a terrestrial acceleration of about 9.8 meters per second, the wavelength is about 7 light years, which is unseeable. But if you were able to boost the acceleration a huge amount, so increase A here, then the wavelength would reduce. And in one experiment, this may have happened. This was an experiment done by Bevis-Lewis and reported on by Igor Smolyaninov, who's shown here. They shone a laser onto a gold nanotip, which is shown in the top picture. The plasmons from the laser went around the bend of the tip very fast, a huge acceleration of about 10 to the 19. And they saw light coming off the tip, which was unexpected. And Smolyaninov managed to show that this looked just like Unruh radiation. So it may have been seen already. So I'm going to use this Unruh radiation, just as I used the ocean waves before, to try and explain the concept of inertia. One of my inspirations for this was a paper by Hai, Schroeder, and Puthoff back in 1994, where they published a very interesting paper attributing inertia to the 0-point field. But they needed an arbitrary cutoff for the 0-point field. And the model I'm going to suggest doesn't need an arbitrary cutoff because it works on a difference in the 0-point field on both sides of an object. So the absolute value of the 0-point field drops out. So that's kind of nice. Anyway, imagine you've got an object shown by the black circle here, accelerating to the right. It sees Unruh waves, which I've shown with the red waves on its right-hand side. Now, between the object and the horizon, the new bit is I'm going to assume that this horizon is able to interact with these Unruh waves and damp them, just like the dock did to the ocean waves, so that only certain Unruh waves can exist between the object and the horizon, like this one, for example, the one shown. If you do this, then there'll be more waves, more radiation in front of the object, pushing it back, than there is behind it, pushing it forward. So there will be a force tending to oppose whatever acceleration you give it. And I managed to show in a paper in 2013 that this looks like inertial mass. And after Jaume Giner corrected a factor of 2, and we published a paper in 2016, it predicts inertia really well. So this predicts standard inertial mass, this mechanism. But that's not the whole idea. There's also another horizon, the cosmic edge. So very far away from us, 10 to the 26 meters, stars are moving away from us, or one of the models is that stars are moving away from us so fast that they're moving at the speed of light and we can't see them. So there's a cosmic horizon. So if an object is accelerating so slowly that its Unruh waves become so long and the horizon it sees recedes so far, as far as the cosmic horizon, then on both sides of the object, the radiation will be equivalent. It'll be equivalently damped. So this mechanism for inertia will tend to collapse at very low accelerations. And I showed this in a paper back in 2007 here. So this is exactly what's needed, it turns out. So what happens is that in the center of galaxies, the acceleration of stars is large, so the Unruh waves are short. But at the edge, the acceleration is very slow. So the theory predicts that the inertial mass reduces, and in fact, it reduces to exactly the degree that the centrifugal force becomes exactly equivalent to the gravitational force. So we have a very nice balance. So I showed that first in a paper in 2012, and then this is a later paper from 2017, where I looked at data from 153 galaxies, and the plot shows the expected acceleration of the stars along the x-axis and the observed acceleration along the y-axis. And the data is shown by the gray squares. And the theory is the dashed line. This is quantized inertia, the prediction, and it agrees with the data. And I should note that there's another theory called MOND, which is shown by the solid line, which also predicts the data. But with MOND, you have to input an arbitrary parameter called A0. So they're able to tune that theory to fit the data, whereas I have no such luxury. The theory has only one chance to be right, and it gets it exactly right. Okay, so that's a paper from 2017. Okay, but the clinching piece of data, and this really means there can be no doubt about this mechanism, is that in the center of galaxies, the acceleration is relatively large, so the Unruh radiation is short. As you move out to larger radii, the Unruh waves lengthen because the acceleration is less. And crucially, at exactly the radius that the acceleration is so low that the Unruh waves get to the cosmic scale, it's at exactly that point that the galaxies start to misbehave. So this is a compelling piece of evidence that the galaxy rotation problem must be due to Unruh radiation and quantized inertia. Okay. Oh, and this point here, I call Milgrom's break, by the way, because the physics sort of breaks and changes to a different regime. Okay, so since then, so that was all about inertia, but it turns out you can derive gravity, Newtonian gravity, in the same way, well, a very similar way. So you start from the uncertainty principle like this, and if you apply it on a macroscopic scale, so on the right I've shown the sun here and the Earth orbiting it. So if you now treat matter as a horizon, so you imagine that the sun is a horizon for the Earth because it blocks the space beyond it, then you'll see that dx is very small between the Earth and the sun, but between the Earth and the rest of the cosmos, the uncertainty in position is going to be very large because it's a large space. So you can put these values into Heisenberg's uncertainty principle, and whenever dx is small, dp is going to be large, the uncertainty momentum is going to be large. So this means that the Earth has a large uncertainty of momentum towards the sun and a small one away from it. So this means that the Earth is going to move towards the sun, a bit like gravity. Well, it turns out that if you do the maths, you come up with Newtonian gravity. It's exactly the same. And I can report as well that in the past week, I've now derived in the same way a variable speed of light version of general relativity as well by this method. Okay, so this is reported in a paper here. I wrote a paper in 2014 on it, and that's the journal link, and there's an animation of it as well on YouTube. Okay, so now I start to get a bit more practical. So if we understand inertia, then maybe we can control it. So the way to do this would be to have an object that you impart a very high acceleration to. So this could be a spinning disk. This could be microwaves in a cavity, something like that. If you accelerate it fast enough, then the Unruh waves will become short enough that they might be damped by, say, a metal plate, something as simple as a metal plate. So I proposed this in 2013 in another paper in 2018. If you can damp these Unruh waves, then it means that, for example, in this case, you've got Unruh waves coming up from below and fewer of them coming from above. So the object will tend to move up. And this is great because it's a fuelless way of producing propulsion. Normally, to get something to move up, we have to blast hot gases out the bottom very fast, which is dangerous, noisy, expensive, and you have to carry heavy fuel. But this would require no fuel. So this would be a horizon drive because the metal plate is acting like a horizon. Okay, so there might be several ways to do this, and I think a lot of effects like this have been seen over the years. So, for example, there was the Pokletnov disk from 1994. So what he had was an asymmetric disk with a very high acceleration, spin acceleration. And the interesting thing for me was that he had a disk with a very small, very fine crystal structure on top and a coarser crystal structure on the bottom. What this will tend to do is to damp these Unruh waves that the material is seeing more above than below. So you would get a gradient in the Unruh field that I've tried to show here with this yellow color. So it's more intense below and less intense above. So this will tend to move things. Things will tend to flow move down the gradient. So things will tend to move up in the vicinity of this disk, as was observed. Okay, so then there was Scheuer's EmDrive. So British engineer Roger Scheuer in 2001, he found that when he resonated microwaves within an asymmetric copper cavity, that looked like this, obviously, called the EmDrive, it tended to move towards its narrow end. And in a similar way, this will tend to cause a gradient in the Unruh field as well, because the narrow end will damp the Unruh waves more than the wide end. So again, you'll get a sort of a gradient that things will tend to fall down towards a narrow end and produce a force in that direction. Then there was Woodward, Jim Woodward from California in the 1990s, and also more recently, he's been looking at asymmetric capacitors. So here's a picture of one of those, vibrating piezoelectric crystals between the capacitors to produce a high acceleration. And in this case, the thick capacitor plate on the left here will tend to damp Unruh radiation more than the thin plate. So again, you'll get this sort of gradient that the object will move down, and indeed, these things tend to move towards the thicker plate. And then there was Thomas Townsend Brown from the 1950s and earlier with his capacitors, and they tended to move towards their anode. And I'll show you a very direct case where this also means that there's a gradient in the Unruh field that pushes it in that direction. But I'll get back to that in more detail later. But I have published papers showing that I can predict the Pokletnov effect, or at least some aspects of it. Scheuer's EmDrive, although of course that's still controversial, and Woodward's Mach effect thrusters as well. So this is some data for the EmDrive. This is a plot showing the thrust predicted by quantized inertia on the x-axis and the observed thrust up the y-axis, and you can see it, the theory does quite well predicting the thrusts. But with the EmDrive, it seems that some groups can detect it and some groups can't. For example, Roger Scheuer obviously detected it. NASA, Harold White at NASA detected a signal and a thrust. Even Martin Timer in Germany did at one point, but now he cannot. And I think NASA had a second try and they couldn't detect any thrust the second time. So it's still very controversial. Okay, so it was about this time that DARPA, I was contacted by DARPA. They emailed me showing interest, and I applied for funding and was awarded $1.3 million to look into this. So DARPA is a Defense Advanced Research Projects Agency, and they've had a hand in things like GPS, the initial versions of the internet, the ARPANET, and stealth fighters. So my project's aims are to make quantized inertia more predictive. So they wanted a computer model predicting the thrust from any given structure, and also to show whether or not it can counter gravity. So they're obviously interested in thrust and launching things with it. So this doesn't mean that I had to launch things, just to produce a thrust in the lab that was obviously due to quantized inertia and that could be scalable to produce a launch later on. So I commissioned some labs, and well, there's a lot I'd like to say about the experiments, but I'm unable to for fear of lawyers at the moment. So there was a test in Dresden where an infrared laser was used and fired into a copper cavity, an asymmetric copper cavity, and it was on a torsion balance, so any thrust on the cavity should have rotated the system, and the system used was a very sensitive one, capable of detecting a few nanonewtons. So the simplest way to say it is that no thrust was detected for this pathway, so we've abandoned it. There's a lot of detail behind that, but I won't say any more. There was also a lab in Madrid, Professor Perez Diaz, shown here, and his team. So what they did was they had a laser. They put the signal into a fiber optic loop with 300 loops, and then placed a metal plate in the vicinity. And the idea here is that Unruh radiation will hit the structure from all directions except from the one where the metal plate is, and it should gain weight. And indeed, it did seem to gain weight by the expected amount in the results from last year. They then put a plate on the other side to make it symmetric, and the thrust disappeared. So these results are encouraging, and the observed force was 0.1 newtons per kilowatt. So you get 0.1 newtons for every kilowatt you put in, which is good. This is better than ion drives, and you don't need fuel. But we're not quite sure about the results yet, so we have to do some more tests on this. There are also tests going on in California at the University of Southern California. So I've been collaborating with Professor David Barnhart at USC and Dr. Ryan Reed with positron dynamics and a few others. And we won some funding from CATIA, which is a Californian aerospace funding body, for them to do some QI cavity tests. But because of COVID, these haven't been done yet. There's been quite a delay, but this would be quite a nice test because they're hoping to use a levitated cavity and then use an interferometer to look for very fine movements. There are also tests being done in Poland by Z Kamala, which are very interesting, but I don't have time to talk about today. And then in 2017, I was contacted by an electrical engineer called Frank Becker. So he'd read my papers on quantized inertia and realized that some earlier experiments he did trying to reproduce the Brown effect, the Bielefeld-Brown effect, could be evidence for quantized inertia. So we talked about experiments using capacitors. Then he received funding and experimental help from Anka Bat, who's actually an actor, but he has an MSc in electrical engineering. And they reported their results on the archive and VIXRA. So they're using capacitors. I mean, I was listening with great interest to Paul's talk just now, and it seems there's a tremendous history behind this that I was only vaguely aware of. What I was aware of was that many groups since the 30s have been looking at capacitors and have reported anomalous thrusts. So T.T. Brown in Paris measured thrust in a vacuum. Canning at NASA in 2003 measured thrust from asymmetric capacitors in a vacuum. Also, T. Musher from Japan measured thrust, but not in a vacuum. And there's a good summary in this paper here, Martins and Peniero from 2011. So the Becker and Bat experiment went as follows. They had a DC power supply, 5,000 volts, and they fed it into a capacitor, which was inside a vacuum sealed container. And the capacitor plates were very close together, a few micron, about 2.5 centimeters in diameter. And they placed the whole thing on a digital scale and they put various voltages in and measured the change of weight. And they measured results like this. So this is taken from their paper. So on the x-axis is the separation between the capacitor plates. So you can see it goes from about 1 millimeter here down to about 1 micron on the left. And up the y-axis, it shows the normalized force. So you can see that the force they got, which is shown by the red dots here, increased as the separation reduced. And because the y-axis is logarithmic, this is actually an exponential increase of the force with the closest of the plate. The interesting thing is that the best result they got for a separation sort of 10 micron is 100 newtons per kilowatt. And this is quite explosive, because if this can be confirmed, then this means we can launch things electrically without rockets. So I'll come back to this in a bit. But the best my DARPA-funded test had achieved so far was 0.1 newtons per kilowatt in Spain. So this is apparently 1,000 times better. So I was very excited by this. Since then, in fact, just this last week, I've been contacted by another team who read a blog that I wrote about this and did a test and got a very similar result. That's the result shown by the black cross here, which tallies with Becker and Batt's data. But the good thing about this new test is that they didn't use a digital balance. I was slightly concerned that electrical effects would be affecting the balance. They used a pendulum and measured the angle of a pendulum, which is a non-digital, non-electrical way of measuring it. So that's very nice. So DARPA have now agreed to allow us to do tests at Plymouth to try and confirm this. So to try and explain what's going on in terms of quantized inertia, the schematic tries to do that. So normally in quantized inertia, an accelerated electron, which is shown by the black dot in the upper picture, would see more Unruh waves in front of it. So I've shown that with sort of warm orange color than behind it, because the Unruh waves would be damped behind it by this horizon shown by the black vertical line. So it would tend to be pushed back by the orange in front against its acceleration, and it would feel inertial mass. But what I think is happening with the Becker and Batt's capacitor is that the electron is coming off the cathode in this direction. But now, instead of seeing a lot of Unruh waves in front of it, it sees virtually none, because the capacitor plates are damping them in front. Instead, now it just sees the Unruh radiation behind, so it's actually pushed forward. So what's actually happening is that the process of inertia has been reversed by the capacitor plates, and the electron has got more momentum than you expect, and then it bangs into the anode and pushes the whole structure forward. So I've done a calculation over the past 2 weeks predicting what quantized inertia would predict for this, and this is the result. So the force you should get should be n, the number of electrons you put in, reduced Planck's constant times the speed of light divided by 2 times the separation of the plates squared. So the x-axis shows here the separation of the plates. The y-axis shows the predicted and observed force. Predicted force is the red squares, and the observed one is the black diamonds with the error bars. So you can see that the prediction agrees with the observed thrust really well. So this is really interesting, because this is a huge force which is launchable. Becker and Batt also did some other things with their experiment. For example, they thickened the cathode. You can see I've shown it in the schematic on the left. And this will tend to damp the Unruh waves on the left even more, so it should reduce the force. And indeed, it did. So this graph here shows the force. These bars show the direction of the force, whether it's forward or back. So initially, they have this big blue bar, and with the thicker cathode, they reduce the force. But the most interesting result probably is the fact that when they put the this metal bar behind the Rindler horizon, as soon as it went behind the Rindler horizon, it had no effect on the experiment. And I should say that this Rindler horizon is not a physical thing. It's a calculated position where this information boundary is. So there's actually nothing there from a physical point of view, just an informational one. And as soon as they put this plate behind it, then the behavior changed, and they got the original force back again. So this is a nice crucial experiment for quantized inertia, and it could be the first direct observation of a horizon. Okay, so I can show you where these results are published on the archive here and on Vixra as well. Okay, so this will be extremely useful for satellites. So this shows a schematic showing a satellite. You have a solar panel here, which has a mass of 20 kilograms and an output of 0.25 kilowatts, taking typical values. And say you put a horizon drive on it of mass 10 kilograms, total weight will look like that. If the horizon drive produces 100 newtons per kilowatt, and we've got a quarter of that, we'll get a force of 25 newtons, which is about 8% of his weight. This is much better than present satellite ion drives, which give only about 0.02 or 0.1 newtons per kilowatt, and they need fuel. Quantized inertia apparently, well, it should, if this experiment is confirmed, give 100 newtons per kilowatt and without fuel. So obviously much better. It also means we can launch things. So if you had a horizon drive with a mass of 10 kilograms and a lithium air battery with a mass of 1 kilogram, that would produce 1.8 kilowatts per kilogram. And if you work everything out, you get a force of 180 newtons upwards, which is more than the weight. So this would enable launch. Okay. So the horizon drive will also give you a very smooth ride, and I've been quite intrigued. I'm not sure whether it's true or not, of course, but the Nimitz UFOs seem to dart around very fast, very high accelerations, and if there was anything in them, surely it would be flattened against a wall. But if, for example, they had a propulsion system like this, then that wouldn't happen. So normally, if you have say a tic-tac shaped spaceship with a flower in it, and you suddenly accelerate it hugely by firing a rocket, then the flower will be smashed against one side of the tic-tac. But with quantized inertia, what you're actually doing is manipulating the process of inertia itself. So the flower would not be affected because the gradient in the Unruh field will affect everything inside the ship equally. So the flower would not be smashed. Okay, so there are other ways to do this. For example, I've recently shown mathematically that if you have a horizon drive small enough on the nano scale, well, that 0.1 micron, then you might be able to produce thrust without power, because just by using the 0-point field itself. So you might be able to design a material, a nanomaterial that self-propels. And I wrote a paper about that called Can Nanomaterials Push Off the Vacuum? And that's in progress in physics. Okay, so you might be able to produce something like this, something that floats without even power. Okay, so applications. The obvious first one is satellite station keeping, far more effective than ion drives. You'd also have to launch lighter satellites. They won't have to carry fuel. Orbital maneuvering would be silent. I've also shown that you might be able to generate power from the vacuum as well using these nano cavities, but I haven't mentioned that in this talk. Obviously, flying cars, new kind of aircraft, structures that hover. So if you can build these nano cavities, you'd be able to build materials that hover by themselves. Obviously, launch interplanetary trips will become easier and cheaper, and it also makes interstellar travel possible in a human lifetime for the first time. Because in order to get to, say, the nearest star, Proxima Centauri, you have to get near the speed of light, and to do that, you have to carry so much fuel that you need to carry a minor planet with you. So this makes it very difficult. But this kind of propulsion will be propellantless, and so you will be able to do that. You'll be able to get close to the speed of light. Okay, so a summary. So quantized inertia explains inertia, obviously. It unifies, in a sense, relativity and quantum mechanics. It uses both of them. It gets rid of dark matter because it models galaxies without dark matter. It has extremely good astronomical evidence. I talked about what I call Milgrom's break that proves it's Unruh radiation that's causing galactic rotation, the effects on galactic rotation. It predicts a very useful horizon drive or electric rocket. DARPA funded experiments, and we're homing in, hopefully, on a successful pathway using capacitors. That's the most successful pathway so far. And DARPA is going to fund an experiment here at Plymouth University to confirm that and try and enhance the effect. So if we can verify this, we'll have fuel satellites, electric launch, and interstellar travel will become possible. The sort of scientific takeaway from this is that quantized inertia says that all movement is caused by horizons damping the quantum vacuum. So let's design technology that taps into this. Okay, so just a sort of contact slide. Thank you for listening, and I can take questions. This is my book. You can contact me by email. My blog is Physics from the Edge as well as my book. I'm on Twitter, and there's a TEDx talk here to watch. Thanks for listening.
Well, Mike, thank you very, very much. Let me mute you out for just a second. I want to go to gallery view. And actually, you know what? I need to, here, I'm going to stop your screen sharing. Let me go to gallery view. And I want everyone to give Mike an enormous applause. Thank you, sir. That was a wonderful presentation. Absolutely wonderful. And actually, I think that's a really brilliant model. I'm really excited by that.